Test chest. Well, let's open the case and see what's inside. Manual. Oh, you won't need that, you're an engineer. Quick guide, signal monitoring, generation, laminated for durability, power supply and battery charger, and the test chest itself. Touchscreen controlled, 800 by 480 pixels, so a nice clear sharp picture. And in the lid, the audio interface, which snaps onto the end of the test chest, toggling for security. But more of that in a moment. Well, we all know this problem. You've been around the back of a bay or inside the desk perhaps. You've got a bunch of cables which are poorly labelled and you need to know what's on them. Here, for example, XLR3. Well, that could be anything from balanced audio to AES. Any of these other cables might contain station reference, video in, video out on any one of several standards. So, how to find out? Well, simple. Just reach for your test chest 3G, plug an unknown cable in, and test chest will tell you if there's anything on it. In this case, 720p, 50 Hz. And I think that's pretty cool. Now I'm going to continue the demonstration of the witch wire, and I've got a number of different video sources here: composite video, standard definition SDI, 720p, 1080i and 3G. I'm just going to apply video inputs to the test chest. The first input is composite video, 625 composite. Powers down, waits its next stimulus, in this case 525 60 Hz SDI, 720p 50 Hz, a 1080 source, 1080i 50, and it's just as fast with a 3G. In this case we've got 1080 progressive A format at 50 Hz. Another of the witch wire's strengths is its ability to differentiate between a picture source and a reference sync source. I'm applying a tri-level sync, which you'll notice is displayed as a waveform rather than as a picture. If I apply colour black to the sync, you'll notice waveform is displayed again, and of course we've got the ability with the on-screen shift to move it around and examine it in more detail. Let's explore the video generation menu. At the top of the frame is a banner which shows the declared output standard and the test signal being generated. I'll leave the pointer on the standard because that'll be changing. We have 4 coarse groups of standards, within which we may select substandards. Where appropriate, we may apply the NTSC multiplier or operate interlace or progressive. Video test signals are selected from the menu beneath, to which may be added a movable puck to help guard against MPEG freezing, a circle with one of 2 aspect ratios, or programmable text, or we may select clapperboard, our unique audio-video timing utility. Using no more than their ears and a TV monitor, users down the line are able to determine empirically audio-video timing errors between the flash at time 0 and the tone interruption. The audio monitoring menu is divided into 2 functions: input selection and metering. Normally, group 1 of the embedded audio is selected by default, but the others may be toggled through if required. AES may be selected, as may external analog. Speaker and headphone selection normally follows the input selector switch. Meter scaling can be varied. Here we've got a British style ppm with ppm4 referred to -18 dB, -20 dB for SMPTE level, VU with VU ballistics, again with variable reference, same again for Nordic. On the digital scale we can alter the gain in blocks of 30 or 60 dB, which would enable us to measure very low signals as from a digital microphone, for example. I can apply an AES signal to BNC3 and select it on the front panel here. Notice the yellow tally warning that this is a non-standard condition. Steady state tone on the histogram and a numeric display at the top here, ideal for level measurement. If I apply a video reference to the witch wire input down on the bottom right hand corner, notice the tally is flashing, which indicates that the 48 kHz is not locked to the video reference, and this of course in program would represent a rich source of audio clicks. Uniquely, test chest interfaces with balanced audio correctly. Here we've a stereo input, which we'll select. Notice the stereo phase indication, which is a feature of all audio inputs on the test chest. Folk are always impressed with the amazing speed of operation of test chest. I've got a demonstration here that's pretty amazing. I've got the output of the first unit connected to the input of the second. If I power this first unit up and change standard, the second unit will respond almost immediately. (720), 1080, SD, 1080, 720, 60 Hz, 50 Hz, 1080i, 50, segmented field 24, and I reckon that's pretty impressive. Time domain reflectometry is a very powerful investigative tool. A fast transient is launched into a coaxial cable, and any electrical rough edges cause reflections that are shown on the display, similar in concept to radar. Now, I've got a demonstration case here containing 50 meters of miniature coaxial cable, at the end of which I can add a further 5 meters of 50 ohm coaxial cable on this switch. I have also a 100mm long stub, that's about 4 inches, which I can switch in via this switch, or I can vary the termination from a precise 75 ohms to a resistor which will vary between about 70 and 80 ohms. I'm launching a 32 nanosecond pulse into the 50 meters of coaxial cable, at the end of which I'll add 5 meters of 50 ohm. That mismatch is clear to see. So too is the 100mm stub. Remember, that's just 4 inches at the end of 50 meters of cable. And if I switch to the variable resistor and vary between 70 and 80 ohms, the mismatch is obvious, and the correct setting is probably about there. Actually, that's very interesting, because you'd anticipate the correct position being about 50% of the rotation. In fact, it's significantly less, perhaps 73 ohms. So that suggests the impedance of the cable is not 75 ohms in this case, but nearer 73. Restricted access and working in your own light? Or too dark to read idents clearly? Then simply use the utility lamp.